In the last video, we talked about how to find solutions to a linear homogeneous differential equation with constant coefficients if the roots to the characteristic equation were real numbers and all different from each other. In this video, we're going to be talking about the same types of differential equations, but we're going to be looking at the case where the solutions to the characteristic equation are still all different from each other, but where they're complex roots. Now, we've dealt with this before with second order linear differential equations when we had, for example, an equation that looked like this: y double prime plus 3y prime minus 4y equals 0. This gives us a characteristic equation of r squared plus 3r minus 4 equals 0. We can factor that. It's just a quadratic, so we can either factor it or we can use the quadratic formula, whichever you're more comfortable with. That should not be a 3, it should be a 4. And we have plus 3, so plus 4 minus 1. That tells us that r is negative 4 and r is equal to 1. So this is a case where the characteristic equation has two distinct real roots, and we have for our general solution c1 e to the negative 4t plus c2 e to the 1t. But what happens when we have a differential equation that looks like this? Y double prime plus y prime plus y equals 0. And I can tell right now, well, let's write the characteristic equation. R squared plus r plus 1 equals 0. This is not going to factor, so I'm going to go straight in with the quadratic formula. R is equal to negative 1 plus or minus the square root of 1 squared minus 4 times a times c all over 2 times a, which is negative 1 plus or minus the root of 1 minus 4 all over 2, which is negative 1 plus or minus root negative 3. Oops, I left my negative off there. Negative 3 over 2, which of course I can rewrite as negative 1/2. Sorry, I've got the wrong pen going here. Negative 1/2 plus or minus the square root of 3 times I, and I'm actually going to write the I in front. The square root of 3 times I all over 2. And that I can rewrite as negative 1/2 plus or minus root, I wrote a 2 instead of a 3 inside my radical there. Root 3 over 2, root 3 over 2, that fraction, times I. So there's my A and there's my B. A plus BI looks like that. This is a complex number. It's actually two complex numbers. It's a plus and a minus. This is one of the reasons we say complex conjugates come in pairs, because there's always a plus and a minus version. Now, I don't want to go into a lot of detail here because we've already talked about what to do with this. It's tempting to say, well, we just write it as y equals c1 e to the negative 1/2 times t plus c2 times e to the root 3 over 2 times I times t. But remember that we also have a way of writing these solutions as with factors of sine and cosine. So the actual solution to this equation is going to be y equals c1 times e to the negative 1/2 t times the cosine of the imaginary part, root 3 over 2 times t, plus c2 times e to the negative 1/2 t times the sine of root 3 over 2 times t. If you can't remember how we got there, this comes from section 3.3 in your textbook. The section title is Complex Roots of the Characteristic Equation. There's a little bit of introduction, and then they talk about Euler's formula. And once you know about Euler's formula and the fact that e to the it can be written as cosine t plus I sine of t, it evolves from there into a different way to write e to the power of a complex number times t. And from there, we get this form of the solution to a differential equation. So that's how we did this back in chapter 3. Let's take a look now at how this is going to affect our work in higher order differential equations. I don't need to do an example of a higher order differential equation, homogeneous linear differential equation with constant coefficients, because we did that in the previous video. So we're just going to jump into an example of the case where the roots of the characteristic equation are complex. So here my characteristic equation is going to be r to the fourth minus r cubed, no r squared term, there's no second derivative term here, plus r equals 0. There is a that should be a 2 right here. Okay, and there is a common factor of r, so I'll go ahead and factor that out. R cubed minus r squared plus 2 equals 0. And obviously one of the solutions here is r equals 0, but the other two solutions, or the other three solutions rather, come from this cubic. So we need to figure out how to break down r cubed minus 2r plus 2. Let's do some synthetic division. I've got r cubed minus r squared, 0r, and 2. My possible rational roots are plus or minus this number over this number. So I have 1 over 1, 2 over 1, plus or minus. And I'm sorry, I should have said plus or minus the factors of this number over the factors of this number. The possible rational roots here are 1 and 2, positive and negative. Let's try 1 to start with. I'm going to just carry this 1 down and then multiply and add, multiply and add, multiply and add, and that is not 0. So 1 is not a root. Let's try negative 1. Drop the first one, multiply, add those two together, multiply, add those two together, multiply, add those two together. We have a 0 remainder here, so negative 1 is a root. That means I can write r cubed minus r squared plus 2 as r plus 1 times the stuff left over. And the stuff left over is right here. I have to go down by 1 power, so I'm going to come down to r squared minus 2r plus 2. I still have this factor of r out front here, which means that r equals 0 is a solution. I haven't forgotten about that one, but what I'm trying to accomplish here is factoring this cubic, so I've left it out for the time being. Now, I could try to factor this, but I can tell by looking at it that it's not going to factor, and from experience. And if you try a couple of attempts, you very quickly realize that either it's not going to factor or it's going to be very difficult to factor, and so you might as well just go to the quadratic formula. So let's do that now. R is equal to negative 2. I said negative, and I just wrote negative. Negative 2 plus or minus the square root of negative 2 squared, that's b squared, minus 4 times a times c all over 2 times a, which is positive 2, plus or minus 4 minus 8 all over 2. That's 2 plus or minus the square root of negative 4 all over 2, which is 2 plus or minus I times the square root of positive 4 over 2, which is 2 plus or minus 2 times I over 2, which is 1 plus I. That's to be plus or minus I. So I have two more solutions here, 1 plus I and 1 minus I. R equals 1 plus I and R equals 1 minus I. So now I have 4 distinct solutions. I have y1 equals e to the 0t, y2 equals e to the negative 1 times t, y3 is going to equal the solution that comes from this complex number. I have e to the 1t. That 1 comes from here. I could put a 1 in front of my i's as well, because I'm going to get a 1 in the next part. E to the it times the cosine of 1 plus I times the sine of 1. That's e to the it times that. And then y sub 4 is e to the 1 times t times the cosine of 1 minus I times the sine of 1. Now our general solution is going to be a linear combination of these, assuming that these are linearly independent, and they are, but I'll come back and talk about that in a minute. Our general solution is e to the 0t, which is, sorry, I need to back up. It's c1 times e to the 0t, and e to the 0t is e to the 0, and e to the 0 is 1. So this is times 1, plus c2 times e to the negative 1t. We'll just call that negative t, plus c3 times e to the t times cosine of 1 plus I sine of 1 plus, close that, plus c4 e to the t cosine of 1 minus I sine of 1. As we discovered in section, I think it was 3.3, this solution works, or it might be more accurate to say that this is a form of the solution to my original differential equation, but frequently, very often in fact, because this equation was given with no complex factors, no element here is complex, we would like our answer also not to have any complex elements in it. But we've figured out how to deal with that in section 3.2 and 3.3. We learned about a theorem that said that if y equals, I'm going to use the function notation that we did in that section, u of t, a function of t, plus I times another function of t, are solutions to a differential equation such as the one we have up here. That original differential equation would be something like y double prime plus a function times y prime plus another function times y, right? Y double prime plus p y prime plus q y equals 0. P and q have to be continuous real valued functions. So that's an important constraint, but we can bypass it for now. If u of t plus I times v of t is a solution to that original differential equation, then just the function u of t and just the function v of t are also solutions. Oh, so I can't spell and talk at the same time. Also solutions. So let's take just y3 here, and we'll do the same thing as we did in the video for section 3.2 where we were discussing this for the first time. I'm going to distribute that e to the t. I get e to the t, the cosine of 1, plus, and I'm going to rearrange the numbers and the factors in this. I'm going to write it as I times e to the t times the sine of 1. And then I've got here an a plus bi. I'm going to put those in a different order, but that's okay. Multiplication is commutative. A plus bi, and what we've got here is that this, let me highlight it, this form of the equation is equivalent to this form of the equation. It's just been distributed and rearranged a little bit, right? Those two things are equivalent. But this is a solution. It's not the general solution. It's just a solution. There's no constant in front of it. It's just a solution to the original differential equation. So this is also a solution to the general differential equation. And this now applies. I can say that y, what shall I call it? Let's maybe call it y4, no, y5. Y sub 5 is e to the t, the cosine of 1, and y6 is e to the t, the sine of 1. I have y equals u plus vi, a plus bi, where a and b are functions, not just constants. Here it is again. Y equals this thing rearranged is a plus bi. So a is my function u of t, and b is my function v of t. So here I have a plus solution y that's a plus bi or u plus vi. If that's the case, then just the function v and just the function u, there's u rather, and there's v. Those are also solutions. So I don't have to write this with an I in it. I can write it a different way, and I can do the same thing with this term here. All right, well, I've run out of room to do this. So what I'm going to do is erase the right-hand side of the screen because that was all just computational stuff that we did way up here. So I'm going to erase most of that. Let's see, I can get rid of all of this. This is just my quadratic formula. That's how I found my two solutions, my four complex solutions. And so now I've got a little more space and I can write the general solution is y equals c1 plus c2 e to the negative t plus, now I'm going to write this is my, let me use a different highlighter here so I can show you. This was my y3, right? So to write that term differently, I'm going to start by putting down the c3, and then I'm going to write y sub 3 this way. Since y5 and y6 are each individually distinct or fundamental solutions, I can write a linear combination of them. I'm going to run out of C's. I went up to 4, so I think I can go C5. C5 goes with Y5. So C5 times e to the t, the cosine of 1, plus C6, e to the t times the sine of 1, plus, now I'm going to rewrite, different color. I'm going to rewrite y4 using the same theorem, using the same technique. I have C4 as my leading coefficient, and then I have C7 times e to the t, the cosine of 1, minus C8 e to the t, the sine of 1. I did not explicitly work that out because the process for working this one out is exactly the same as the process for writing this one in it without the I in it, right? So now, just to tidy things up, I can say that y is equal to c1 plus c2 e to the negative t, terrible e, hang on, e to the negative t plus, if I distribute, and I get a constant times a constant. I'm going to call it c sub 9, why not, times e to the cosine of 1, e to the t, cosine of 1, plus c sub 10, I guess, times e to the t, sine of 1, plus c sub 11, e to the t, the cosine of 1, minus c sub 12, e to the t, the sine of 1. Now, I've done that, just, c sub 3 plus times c sub 5 is some other constant, and I've just called it constant 9. It really doesn't matter. Ultimately, in the end, if you would like, you can say that this is my solution, but since constants are just constants and I don't know what they are anyway, I can choose to rewrite it as C1, C2, C3, C4, and so on. C5, C6. Oops, that's a minus. That should be a minus. So that's another way to write it. I'll go ahead and put that in a box as well. But we're still not quite done because there's one more thing I could do. And that is, let's see, what shall I erase this time? I don't know that I really need to. I'll rewrite this one more time as y equals c1 plus c2 e to the negative t plus, notice that I can factor e to the t out of all four of these. So I'm going to go ahead and do that. And I'm left with c3 cosine 1 plus c5 cosine 1. That's c3 plus c5 times cosine 1 plus c4 minus c6. c4 minus c6 times the sine of 1. And that is equal to c1 plus c2 e to the negative t plus e to the t times some constant. I'm just going to go ahead and call it, I'll call it c7, why not? c7 cosine of 1 plus c8 sine of 1. Okay, one constant minus another is still a constant, right? So just giving it a different name. That might be a negative number, in which case this would be minus the absolute value of that, but that's okay. C8 can be a negative number. We can handle that. So this is kind of my most preferred version of the answer in that it's the cleanest, right? Look how little space that took up as compared to these two versions. And those are even shorter. Well, they're maybe about the same length as these. Maybe they're a little longer than this one, but this one's got eyes in it. So that's its own problem. These two don't have eyes in them, but they're a bit messy. This is just a little bit cleaner. Now, there's really nothing we have done here in the last, I don't know, maybe 5 minutes or so that isn't just algebra, right? We're just saying that two constants added together are a constant. Two constants multiplied together produce another constant. You can factor e to the t out. You can, this was a little bit new, right? Changing this cosine a plus I sine of a into a different form. That was newer. We learned that in the last chapter, but it was newer information. But we really haven't learned anything new, except that we can perform this kind of operation, or we can solve this kind of problem if the differential equation it has a power higher than 2 now. Nothing really here is new, except that the whole thing is a bit more complex because there are more moving parts, right? You still take your equation, write a characteristic equation. If it's homogeneous, you set the whole thing equal to 0, and you solve the characteristic equation to find your solutions. You write out e to the r of t for each of the 4 r's. If you have complex solutions, you write those in a different form. And then you can further split those up into, not only do they not have eyes in them now, but they are separate solutions in their own right. So the whole solution can be written as really quite simply here. So we haven't really done anything terribly new. We have taken what we learned about complex roots of the characteristic equation from chapter 3, section 3.3, and we've applied it to higher order differential equations. In the next video, we're going to be looking at what happens if those roots repeat each other. So if you had something, for example, like a characteristic equation like r squared plus 6r plus 9, if you factor that, you get r plus 3 quantity squared. So you have repeated roots of r equals negative 3. So that's what we're going to be looking at next.